Hey, welcome. Welcome to the 7th lecture in the design of embedded and intelligent systems. Today we're going to talk about math. So we've talked about hardware and software, and now we'll talk a little bit about different kinds of math that we can use for our systems. So to build embedded and intelligent systems, we need to work with lots of changing numbers. How can we do this? We can use linear algebra and calculus. When I was studying math, I think I didn't really always know why I was studying what I was studying, so in this lecture I'm going to try to explain some of the motivation why you want to use this kind of stuff as well. We'll start with some basic stuff. So for example, matrix vector multiplication, derivatives, integrals, and partial derivatives. So when we want to multiply vectors or matrices, well, matrices in this case, you can see that we multiply the columns on the right by the rows on the left, like this. So if we have 1 and 2 and 5 and 7, then we'll get something like 19. For the derivative, if we have something like pi r squared, we'll get 2 pi r. Integral, the integral of 2 pi r, we'll get something like this, pi r squared plus some constant. And partial derivative with regard to r here would be 2 pi rh. Let's look at some vectors. Let's say we have two three-dimensional vectors and we want to find the angle area between the two vectors and also a normal vector. How can we do something like that? Well, we can use the dot or cross products. So what is the dot product? It's defined here on the left, and the cross product over here. So from this you can calculate using cos or sine. You can calculate the angles. The area can be calculated. The area of the parallelogram between the two vectors can be calculated with a cross product and also a normal vector. So a cross product of b will give you the normal vector to that. Next problem. Let's say we have some data and we want to reveal its internal structure. For example, this can be the axis of rotation for a transformation or some unique structure to represent a face if we're recognizing different people's faces, or how to diagonalize a matrix if we want to take the power of a matrix, for example. Diagonalizing is very useful. How do we find where the most variance in the data is for principal component analysis? So we can maybe reduce the dimensionality to visualize some data to understand it better or to select some features. What can we do for this? Well, if our assumptions are met, we can use eigendecomposition. And what is this? Well, we can find eigenvalues and eigenvectors of a square normal matrix. If we've got a different type of matrix, we can use SVD, singular value decomposition, and we can see sort of some of the equations that we use with for finding the eigendecomposition over here. This is the characteristic equation. So if we have this matrix A that we're analyzing and we multiply it by an eigenvector, it will equal an eigenvalue times the eigenvector. And when we want to find the lambda, the eigenvalues, we can use this equation over here. We find the determinant of the matrix and set it minus this lambda times the identity matrix and set it to equal to 0 and then solve for lambda. And then for each lambda that we find, we can plug it in and again set this equal to 0 and find the eigenvectors that satisfy that. And this is the singular value decomposition over here. Here's another common problem, I think, in In designing embedded and intelligent systems, we want to make some type of change of variables, or we want to describe the local behavior of a function. For example, we want to calculate the speed or torque to move a robot's joints, or we want to track a robot using extended Kalman filter. How can we do this kind of thing? Well, we can use a Jacobian. So what is a Jacobian? Well, it's sort of like a generalization of derivatives and gradients. So for example, here we have something like x squared, where we can take the derivative to get 2x. If we have a gradient, maybe we have sort of like a vector here. And if we have a Jacobian, we'll have a matrix of the partial derivatives. So for a change of variables, for example, you can see examples here where we're finding the speed of the end effector using the Jacobian multiplied by the speed of the joint angles, or we're finding the force over here. So the force we have to give to the joint angles to get a force at the end effector. And just to give an example here, if we have two variables and two functions, then we can calculate the Jacobian like this. We just calculate the partial derivatives of the two different functions by the two different variables. And then when we get this determinant, we can check what happens at a certain point. So if the determinant is 0 at that point, the function's not invertible at that point. If the determinant is greater than 0, then the orientation is preserved, less than 0 reversed. And the size indicates expansion or shrinking. So if it's less than 1, it's shrinking. If the absolute value is greater than 1, it's expansion. Sometimes we want to find a local minimum of something. For example, if we're doing backpropagation for some deep learning or neural networks, or if we're doing quadratic minimization with least squares, how can we do something like that? Yes, you guessed it, gradient descent. So how does gradient descent work? Well, we can use an equation like this. So we can iteratively move towards this local minimum, where we have the next position will be the last position, and then taking a step down the gradient, down the slope of our function. Now here's an example. If we start over here, then we calculate the gradient like this, and we move a certain distance gamma down that, which can vary over time as well, the learning rate. Another kind of really useful thing to do is to think how we can approximate some type of complicated function, maybe around some local place, around a point. For example, for extended Kalman filter. One thing we can try is a Taylor series. So what is that? We can use this equation over here. To approximate f of x, we can say that it's equal to the summation of the nth derivative of the function at a times x minus a to the n over n with this bang. So that's n times n minus 1 times n minus 2, etc. The factorial. Here's an example. So if we have, for example, f of x equals sine x, and we use a first order approximation, so we just calculate the first derivative and no further, then at a equals 0, we get something like f of x is approximately sine 0 plus cos 0 x minus 0, and sine 0 is 0, cos 0 is 1, so we get x. And what does that mean? Well, it's quite intuitive, because if we look over here, then this basically the more terms you use, the more it will approximate the sine wave. If we're only using one, it's very basic approximation around this area of 0. So it's basically the slope over here, the tangent. Same thing for 90 degrees. If we go to 90 degrees, then we calculate this and we get 1. So that's, again, cutting across there. So the slope over here, and we'll get the same thing if we keep going down there. Well, with embedded and intelligent systems, we also work with images a lot, but how can we work with the local structure of an image, for example, to smooth an image or to find edges or objects within that image? Convolutions are very useful here. So how do we do this? Well, we can just take a moving window and pass it over our image. Like over here, for example, we've got this window and we pass that over our image. And then we multiply the associated terms and add them. And then we would come up with this result if we were multiplying, if we were convolving this image with this window. I think this is another nice example for embedded and intelligent systems. Sometimes we want to be able to move from some measurements to a prediction. Here's an example. We want to predict how fast some robots are. We call that B hat. We have some measurements for robots, like their weight, their power, the motor torque, and speed. So the speed will be the real B, and the other variables we can put in A. And then we want to know how we can go from some type of function of A to our prediction, a good prediction. What is this problem? It's a linear least squares problem. If we define it the way we do here, we assume that this function of A that we're looking for is a linear function. It's so we can say it's A multiplied by X, where X is some type of parameters to try to predict B. Then we can define the residual to minimize R, and then we define that as B hat minus B equals AX minus B. Then R squared will be a scalar. So it's the transpose of R times R, which is great. And then we want to find basically the X that will minimize R squared, their squared residual. So I've just sort of laid out the variables here in a little bit of a clearer way. If you want to try this problem yourself, you can use these hints over here to try. So I'll assume that you've tried this problem if you want, and then I will go on. First, we want to simplify R squared. So we substitute this in and we expand. This is the transpose. And this is fairly straightforward, but here we get these two terms. And then there's a little bit of a trick. The trick is to realize that this will be a scalar. So the order doesn't matter, and we can group those terms and simplify a little bit more. So we get that, and then we want to set the derivative, take the derivative and set it to 0. And using our hints, we can do so. So we take the derivative of R squared with respect to X, and then we simplify, and we can get this answer for what X should be if we can take the inverse. So this is called the pseudo-inverse, and it pops up quite a bit in different places. Next, how can we minimize a function that has constraints? For example, in support vector machines, we want to minimize something subject to another equation. Well, one way to do this is as follows. We can use a Lagrangian multiplier, the Lagrangian dual. So we have some system of equations over here. We have f of x such that g of x equals a. And then a way to approach this is to define L as a function of x and lambda as equal to f of x minus lambda gx minus a. And then calculate the derivative of L, set it to 0, and then we can rewrite in dual form. And hopefully get rid of some variables. And that's exactly what we do with SVMs. So, do you want to try this practice problem with matrices? Finding eigenvalues and eigenvectors. If you want, stop the video now, otherwise please go on. So when you attack this problem, you find that the eigenvalues are going to be 1, 2, and 3. And if you have a bit of experience with this, you would have just been able to say this off the top of your head, because in a diagonal matrix, the eigenvalues are these values on the diagonal. And then we find the eigenvectors for each eigenvalue. So if we're looking for lambda equals 1, then we subtract by 1 along here, and we can find this eigenvector. 2x3 equals 0, so we know this is 0, and then we know also that x2 is 0, and we just don't know x1, so x1 is x1, and that gives you this vector. And then over here for lambda equals 2, we do the exact same thing, and you will again see that x3 equals 0, so we set that to 0, and then we have negative x1 plus x2 equals 0, so x1 equals x2, and then we have the same kind of thing for lambda equals 3. Let's try another sample problem. So we've got an example of a Jacobian problem. So please try to calculate the Jacobian determinant for this. And for this we can do some vector calculations. So we want the dot product and cross product. And you can see here we've got hints again on how to do that. So I assume you've paused the video if you wanted to. Let's go on. So here you can see the solution. We just take the partial derivatives of each function with regard to each variable, and we get this matrix over here. We calculate the determinant. So to calculate the determinant, we multiply this minus that. That yields y minus x. And then we can further try to analyze what happens around different points when x is 1 and y is 1, for example. Then the determinant would be 0, so it wouldn't be invertible there. Okay, dot product and cross product. So here I've calculated the dot product and also the angle, and the cross product will give you k with area 1. Okay, so hopefully you followed along with this. Thank you very much for listening. See you.